Can we restart? Actually, I realized that I made 2 hours in the previous lecture, so this will be shorter, probably. So what I want to, so this will be more a practical lecture. I think we will need the definition of the dynamical matrix. So I rewrite it here. And what we do now is to discuss in practice how we do this calculation of phonons. Now the difficult theoretical part, I think, is concluded. And now I think that the concepts are, some of them at least, are well known to you. The plan of this lecture is this. We first discuss the phonon interpolation and how we calculate the phonon dispersion. So what we have discussed so far is the calculation of the dynamical matrix at a given Q. But to have a dispersion or to do an integral over the Brillouin zone of some quantity that require the phonon frequency, we need many, many more frequency and eigenvector on all the Brillouin zone. And so it is not practical to use this dynamical matrix for all the wave vector and Q point that we need. It is better to calculate with density functional perturbation theory the dynamical matrix in a grid of Q point and not very big, and then calculate from there the interatomic force constant, and using the interatomic force constant, computing the phonon dispersion at all the Q and the frequency in all the Brillouin zone. Then I will discuss a few ideas on the phonon Q vector parallelization and how this is implemented now in the phonon code. And I will also show you a new code that has some new feature for the parallelization Q vector. Then I want to discuss a little bit which kind of thermodynamics you can study by using the phonon frequencies. And we will discuss the canonical partition function and a few thermodynamic functions that you can calculate at a given geometry if you calculate the phonon dispersion at that geometry. Then there is the next question in thermodynamics, what can you get if you calculate the phonon frequencies at several geometry? So in that case, you can have also information on partial information, at least, on anharmonic property within the so-called quasi-harmonic approximation, where you assume that the frequencies depend on the volume or on the geometry of your solid. And you can calculate another set of quantity also within this quasi-harmonic approximation. And so we will discuss also this. So point number 1, the phonon code. So the phonon code is called ph.x in quantum espresso. And what it does is it sets up this, so it reads the input of PW. So first you have to do a self-consistent calculation with PW. And then the charge density, the wave function, the geometry is written on a file. This phonon code reads this file, set up the dynamical matrix with the expression that we have seen this morning. Is solved for each perturbation. So we need the perturbation mu, basically for each Q vector, for each S prime atom, and for each beta. So for each Q vector, we need 3 multiply the number of atom perturbations. And we need to solve a self-consistent linear system, in principle, for each one of these perturbations. Find the response of charge density for each one of these perturbations, where an atom 1 moves in direction x, atom 2 moves in direction y, and so on. Actually, what the phonon does is to do linear combination of this displacement that transform into themselves according to the symmetry of your solid. And so it makes a few perturbations together, moving more than one atom in particular directions. So that when you use the symmetry that transforms a Q into itself, also these modes goes into themselves. Unfortunately, you have to set up, to carry out the linear system for all the modes that mix among themselves if you want to use symmetry to reduce the amount of calculation that you do. In any case, conceptually, we have for each Q to do 3 multiplied number of atom modes. And we will obtain, when we have done all the 3 multiplied number of atoms in the unit cell perturbation, we will have the dynamical matrix, and diagonalizing it, we find the frequencies at that Q, and we have 3 multiplied the number of atoms in the unit cell. We will do the example of silicon that has 2 atoms, so there will be 6 modes. 3 multiplied 2 is 6, and 6 frequencies for each Q. And in principle, if you repeat this procedure for all the Q along a path in the Brillouin zone, you can plot a dispersion. But to do that is possible, but not very convenient. And so what we can do is to use these ideas. So the dynamical matrix we have written like this. And you see from this expression that the dynamical matrix is a periodic function. So if you think of the dynamical matrix as a function of the wave vector Q, it is a periodic function with periodicity the reciprocal lattice vectors G. Because if you put here Q plus G, e to the I G R nu is 1, e to the I G R mu is 1, so you obtain the same expression. So the fact that you have a periodic function allows you to do a Fourier transform, basically. And so you can see equation 1 as a Fourier expansion of the dynamical matrix, and the interatomic force constant are the Fourier coefficients. So you can write the expression of the Fourier coefficient using the usual, so if you have a function f of x in one dimension, such that f of x plus a is equal to f of x, usually the expansion in Fourier series means that f of x is equal to sum over L of f of GL e to the I GL x, where GL is 2 pi over a multiply an integer L. And the expression of f of GL is 1 divided omega, 1 divided a, the integral from 0 to a of f of x e to the minus e GL x dx. And actually here it is the same, only that we have a three-dimensional function that is periodic with the periodicity of the Bravais lattice. So the interatomic force constant, we have to integrate over a period, and the period is a Brillouin zone, d3q, divided the volume of a Brillouin zone, that is 2 pi cube divided the volume of one unit cell. And then we have to integrate in D3Q and put here with a minus sign EQ R nu minus R mu. Yeah. Yes. No, basically I think it disappears because it is not there, because there is a sum over nu. So in any point that you look, when you sum over all the other points, and there is a phase that depends on the distance between the first point and the second point, the interatomic force constant also depends only on the distance. So why there should be a dependence on mu? No, you don't have because it is independent. You can put, if you want, a sum over mu and 1 divided n, the number of cells. But I choose one particular mu. And since the thing is independent on the particular mu that you choose, you do the sum. You don't write it there. I mean, they are all equal for all mu, I think. Okay. Provided that the sum is large enough. So here we are summing over all vector nu, and given a mu, you have all the nu that are around for which the interatomic force constant are different from 0. Okay. And so this is the expression of the interatomic force constant. And now the point is that we can do this integral numerically. So we can choose a given grid of Q point and discretize this integral. So let's see in one dimension how this discretization works. So suppose that this function f of x is known from 0 to a on a mesh delta x equal to a divided by n, and xi is equal to e, or let's call this xj, j delta x. Then this integral, that is the Fourier transform, is discretized as 1 divided a, sum from j that goes from, let's say, from 1 to n or from 1 to n. And f of x j e to the minus I. GL is 2 pi over a L, and x is j delta x, so a divided by n. And then we have to put delta x, that is a divided by n. So we obtain 1 over n, sum over j, f of xj, e to the minus e, 2 pi over n, lj. So you see that this is the expression of the Fourier transform, and this, let's say, is its approximation. F tilde of GL is its approximation if we take a discrete set of points, and if we know the function fx on this discrete set of points. So this is the same idea here. We calculate the dynamical matrix on a discrete set of points, and we will obtain its Fourier transform into an approximation of its Fourier transform. And look at this Fourier transform. Well, what happens here is that f tilde of GL plus n. So if I add n to f tilde, to the index of GL, I have F tilde of GL. This is simple to prove. Put here F tilde of, it is 1 divided by n, sum of j that goes from 1 to n, fxj, e to the minus e, 2 pi over n, L plus n, j. Pi over n, j. And then here there is 2 pi j, n and then simplify. And 2 pi j, this is an integer, so it is equal to 1. So this is equal to f tilde of GL. So it means that if this is the f of GL, the true Fourier transform, that usually for a sufficiently smooth function goes to 0. So if the dynamical matrix is a sufficiently smooth function of Q, the interatomic force constant in principle should go to 0. If we discretize them, we find something like this. So the discretized form has some value that are similar to the real Fourier transform, close to the origin, but then after n points, it is periodic, so we will get the same. This is f tilde of GL. So if from minus n divided by 2 and n divided by 2, the real Fourier transform went to 0. So if we take a grid of Q point such that the interatomic force constant outside this range are 0, well, with this function that becomes periodic after n, we can approximate well the real Fourier transform, so the real interatomic force constant. Otherwise, we have what is called the aliasing error. Some of the component of the real Fourier transform that if they are different from 0 outside of this interval, you find them inside here, and so the approximated Fourier transform is not a good representation of the real Fourier transform. And this, in principle, depends on how large is the range of the interatomic force constant. But in principle, increasing the size of the grid, you can find a grid that is sufficient to have all the interatomic force constant. This is true. So let's suppose that this happens. Then we can approximate the interatomic force constant with a function like this. This C is the dynamical matrix multiplied by the masses. So it will not have the masses. And basically taking the dynamical matrix at a grid of Q point and summing over this Q point with this Fourier component here, with this phase factor here, we should obtain the interatomic force constant for a certain number of neighbors. Interatomic force constant that are periodic then in real space. However, if the real interatomic force constant went to 0 outside the range where these are defined, with this approximated interatomic force constant, we can approximate the real one. And then we can use this interatomic force constant again to calculate yes, this is the expression if you don't put the index mu and use the index 0. But then, once you have the interatomic force constant, you can recalculate the dynamical matrix at an arbitrary Q with the Fourier series. And here you will have the approximated interatomic force constant. If the real one went to 0 when this reappear large for periodicity, and here you sum only on the R where you have calculated the interatomic force constant, you get a good expression for the Fourier transform. So, there are two codes that we have that does this. Q2R is a code that reads the dynamical matrix that we have calculated with DFT in a grid of Q point, and gives the interatomic force constant for the shell of neighbor that correspond to this grid. And this is an information that we have to give as an input of the Phonon code, what is the size of this grid of Q point on which we calculate the dynamical matrix. Then Q2R reads this size, reads all the dynamical matrix computed by the Phonon code, and gives the interatomic force constant. Once we have the interatomic force constant, the approximated one, because this is done on a grid, on a finite grid, we can use a Fourier transform, and this is another code that is called matdin.x, reads the interatomic force constant, and makes a Fourier transform. So you basically use this formula here to calculate the dynamical matrix in all the Q vectors that we want. And so doing this trick, basically, we can have the phonon in all the Brillouin zone, and we can do a plot by using a path in the Brillouin zone, or we can do a much thicker mesh of Q point and do integrals over the Brillouin zone of the frequencies or of function that depend on the phonon frequencies. We can also calculate the phonon density of state, for instance, that is an important quantity that allows to calculate the thermodynamic quantity. So there are two cases in which this approach fails. Well, one case is when the dynamical matrix is not smooth. So if this function has some is not smooth for some Q point, probably the number of Q vector that you need to describe very well this small feature is quite large, and so there you need to increase a lot the mesh of Q point. And this happens in metal when there are cone anomalies. There are another case in which these things are not work very well if there is some non-analytic part in the dynamical matrix, and this happens in polar insulators when you have electrostatic interaction. But luckily, it is possible to write an explicit form of the non-analytic part of the dynamical matrix in terms of the electric constant and Born effective charges. And so one can subtract the non-analytic part, do this trick for the analytic part, reinterpolate the analytic part, and then add again the non-analytic part to all Q points. Since the non-analytic part can be calculated very easily, one can use this trick and interpolate the interatomic force constant also in polar insulators. Okay, use of symmetry. So, there are two possibilities. So, when we calculate the charge density in the PW code, rho of R, you have to do a sum over k vector in the first Brillouin zone of the wave function phi k v square modulus. And basically, you don't do this sum adding all k point, but reduce the k point with the point group symmetry of your system. And then you do this sum and calculate the bands only on the irreducible part of the Brillouin zone. So you can reduce a lot the grid of k points. In principle, you like the same when you calculate d rho over d mu. And you have to do a sum over k and v of this dc. Let's say we wrote this. Or better, we wrote an expression with 4 times u k v star, and then there was p k plus q c du k v over the periodic part of this u q s s prime beta q. So this was the expression of the change of the charge density that we wrote, and in principle also here we have to do a sum over the k point. The problem is this, that if we want to use the full symmetry of the point group to calculate this change of the charge density, well, there might be some symmetry operation that when applied to a q gives a different q. And so in this case, we would need the perturbation with respect to rotated q vectors. The choice of the phonon is instead to use not all the point group symmetry of the system, but only those that, such that when you apply to a q vector, gives the same q vector, maybe in some cases plus a reciprocal lattice vector. And so the k point that you need here are more than those that you use for the self-consistent calculation, because they are reduced not with all the point group symmetry of your system, but only with the symmetry of this is called the small point group of the q vector. And this has less symmetry, and meaning that this has more k point. And so the Phonon code make a non-self-consistent calculation on all the missing k point and on the k point k plus q. This is one choice. The other choice is to bring all the perturbation at the q and at the rotated q vectors. All the rotated q vectors are called the star of q. And this was in the original version of the Phonon, but then it was found that it was not very convenient. It was more convenient to do a single q vector. But the more the q vector is in non-symmetric point in the Brillouin zone, so suppose it is a generic q vector, then when you rotate it with the point group symmetry of your solid, you obtain a lot of q vector in the star. And this means that there are the small point group of q is very small. So you need a lot of k point because the point group of q is small. So for non-symmetric q point, you need a lot of k point. But you have an advantage that when you have calculated the dynamical matrix at a given q, you can use symmetry to calculate the dynamical matrix in all the rotated q. And so there are q vectors that require more time and q vectors that require less time. In general, the amount of time that you need maybe can be estimated like this. The total number of the grid of the point of q times 3 number of atoms times something proportional to the time for a self-consistent calculation. And the more asymmetric is a given q, the more it takes a larger part of this time, but it gives you more dynamical matrices. So what we do is we do a uniform mesh of Q point, but we do not calculate all these Q points, but only those that are not equivalent by a symmetry operation. So we have to calculate only a reduced set of Q points. And then rotating the dynamical matrix in this reduced set of Q points, we get all the mesh of Q points. And what we do is that we choose for each Q point displacement pattern that transform according to the irreducible representation of the small group of Q. What you can show is that the number of these irreducible, the number of modes that transform among themselves depend on the size of the irreducible representation of the small group of Q, and in general, the maximum for a normal Q point is 3. On the border of the Brillouin zone and for non-symmetric point group, you can arrive up to 6 modes that you have to do together. For the OH group, however, this is a very, very rare circumstance. And usually 3 or sometimes 4 or less modes together make an irreducible group of modes that you have to calculate. So now parallelism. So it is clear that, the Phonon code is parallelized as PW. PW, you will see probably in the next week, is parallelized on G vector, is parallelized on K point. But now, and is parallelized on band, on task group, on many, many, many things. In the Phonon, there is the possibility to make another 2 levels of parallelization. In principle, we can do we have to do first a self-consistent calculation. Then we have to do we can do a serial calculation where we do a loop over the Q vector, calculate the bands at K plus, at all the K that were not in the original set for PW and on the K plus Q. And then we can do a loop over the irreducible representation that have to give the 3 number of atom modes. And we do one after the other. One Q, all the irreducible representation for the bands, and all the irreducible representation of that Q, and so on. One after the other, you do all the calculation until one finish. But there is the possibility to parallelize over Q. Basically, you can send in different machines different Q vectors. So you do one Q vector in a set of processor, another Q vector in another set of processor, another Q vector in another set of Q vector. And each Q calculation, you have to calculate the band, then do the loop over the irreducible representation, one after the other, until you finish all of them. And then you have the dynamical matrix at all Q. You can also parallelize in a third scheme in which you send in each set of processor the Q vector and the irreducible representation. Here you have some overhead because you have to calculate the bands for all the irreducible representation. If you do it, each irreducible and each Q in different computer, in different set of processors. And then after this step, you have to collect the results. Once you have collected the result, you can calculate the interatomic force constant. You can calculate dynamical matrix in all the Q vector that you want, and in principle, you can calculate the thermodynamic quantity at this geometry. So there are, in the input of the Phonon, there are, I would say, 3 ways of doing this parallelization. One is to use the Phonon code and use these flags start queue and last queue, where you say in the input which queue in the mesh of queue point of the inequivalent queue point, which one you want to really calculate. And you can say if start queue is 1 and last queue is 1, you do the first queue point. If it is 2, you do the second queue point, and so on. In principle, you can send this in different directory, even in different machines, and then collect the dynamical matrix for each queue. This is called the grid approach. You can do also the parallelization of the irreducible representation using start ER and last ER. And so with these 4 flags, start Q, last Q, start ER, and last ER, you can say to the phonon, do that Q point and that irreducible representation of the Q point. You can do more than one on the same run, several representations, or I don't think it's very useful to do few representation for a set of Q points. It is better if you want to parallelize in this way to do one Q point and all the irreducible representation. So the point is that when you parallelize on the Q point and on the irreducible representation, the code makes produce its partial dynamical matrix file in the Scratch directory inside this directory called .phsave. And you have by hand to copy this file into the outdir where you will run then a run of pH that collect all the results. So the machinery there is an example, a grid example that does this, but the machinery is slightly complicated. And relies a lot on the fact that the user must know what he is doing. There is a second possibility that is the image parallelization. So you can run the Phonon code using -ne number of images. And basically, the tasks are divided by a driver of these images by the phonon, basically, that gives to each images a certain number of Q points, and depending on how many they are, it divides the total amount of work. That can also be divided, if you want, with start Q or last Q, but this complicates a lot the thing, but in principle it is possible. And then every group of processor, each image, will do a given representation, a certain number of representation for a given Q. At the end of this calculation, you have only to collect the result produced by the different images. The images already write everything on the directory of the image number 0, and you need just to run pH another time after this calculation. There is now a new code that is called thermopW that does this all automatically. And basically, you give the number of images, and it collects the result, and it presents you with the final phonon dispersion, so you will not have to take care of all the machinery, of where the files are. It is, however, a little bit less flexible than pH, and could be convenient if you have a machine that is able to do an entire dispersion in a single run. Otherwise, the recovering here is still in a worse status than pH, and so probably it is still better to use the Phonon code to do this. Okay, that's all I wanted to say on this. And now the question of what can we do when we have the frequencies? What kind of quantity can we calculate from the phonon frequencies? Well, now what one should do is to take the Hamiltonian that we wrote for the nuclei, and having the phonon eigenvectors of the dynamical matrix and the phonon frequencies, it is possible to rewrite this Hamiltonian and to show that it is equivalent to a sum of harmonic oscillators. And then you can quantize these oscillators so that the total energy of the phonon system can be written in terms of the frequency like this, as a sum over all the Q vector and all the frequency of some integer number, n Q nu, plus 1/2. Basically, this integer number says how many phonon of a given frequency are present in your system. And actually, one cannot solve really the dynamical problem having the starting position of the nuclei and the velocity of the nuclei. What one can do is to say that you have your phonon system at a given temperature. And so you can use statistical methods to calculate what is the average, for instance, of the energy of this system of phonons, or which is the free energy, the entropy, or the thermodynamical quantity. Well, if the energy is that one, you can use a simple Boltzmann factor to say that the probability that the phonon system has that energy epsilon I is given by E to the minus beta EI divided by the sum over all possible I, all possible state. All possible states are given by that number, integer number n there, that can go from, for an harmonic oscillator, are integer, and goes from 0 to infinity. And here you have to do this sum of E to the minus beta epsilon E. And this sum is called the partition function Z, where this beta, depends on temperature, is 1 divided the Boltzmann constant multiplied by T. So it is simple to calculate this partition function. What we have to do is simply to put here the expression of the energy, e to the minus beta, and here we have the sum over Q and nu of n Q nu plus 1/2 h bar omega Q nu. Now, the exponential of a sum is the product of the exponentials, so we can bring this down here. Product Q and nu. And basically, this sum over this state means that we have to sum over all the possible integer number for each mode. And one can show that this is equal to the product over Q and nu of the sum from n that goes from 0 to infinity of this e to the minus beta n plus 1/2 h bar omega Q nu. You convince yourself that you can exchange these two sums, taking a few phonons and for instance, two phonon frequency, and looking that this product of this sum is equal to the sum of this product. And so this is a geometric series. So we can say that this is product of Q and nu of e to the minus beta divided by 2 h bar omega. And then we have sum over n that goes from 0 to infinity, e to the minus beta n h bar omega q. So this is a geometric series with written like this, usually q n goes from 0 to infinity, where this q is equal to e to the minus beta h bar omega q nu. And this is equal to 1 divided 1 minus q. You know that for a geometric series, one can write that expression. And so basically this term, z, is equal to product of q nu e to the minus beta divided by 2 h bar omega q nu, and divided by 2 we have written, and here 1 divided 1 minus e to the minus beta h bar omega q nu. So it is convenient now to calculate the logarithm of this z, so that this product becomes a sum of the logarithm of this. And now you have several expressions that you find in the papers. They are all equivalent, basically. One way is to take this exponent and divide here. So this will become sum over q and nu of the logarithm. So you bring this down, and it becomes 1 divided e to the beta divided by 2 h bar omega q minus a to the minus beta h bar omega q divided by 2. And this is twice the hyperbolic sign of this. There is a minus here in front because this sinus was at the denominator. Or you can develop the logarithm, and so you develop the first term, and it gives beta divided by 2 h bar omega, and then minus the logarithm of the denominator. They are all equivalent expressions. And basically, the vibrational energy of the solid can be written like this. So if you have the probability that a given state have energy epsilon e, and you want so this is e to the minus beta e divided z. And if you want to calculate the average energy, you do the sum over e of EE, its probability, e to the minus beta e divided z. And this is minus the derivative with respect to beta of the logarithm of z. So look at that. This is the total energy of our volume V, our big volume V. And so if we want to calculate the vibrational energy of one cell, we have to divide by the number of cells. So I put there this 1 over n, and we obtain the vibrational energy of one cell. Since PW writes the total energy of one unit cell, it is convenient that we also work here with the vibrational energy of one unit cell. And so we divide by 1 divided the number of cells. As you know, if you take the logarithm of z and divide by 1 over beta, you obtain the free energy. The free energy is defined as the vibrational energy minus T and the entropy S. Yes, you can also so there are, I don't know if for instance, you can also say that the entropy is defined as minus dF over dt. So it is minus dF over d beta multiply d beta over dt. So d beta over dt, beta, we said, is 1 over kb t. So d beta over dt is minus 1 divided kb t squared is minus beta divided t. So this we can write is minus beta divided t. And so if, so just to convince that f must be this object, even if you can demonstrate in many ways, it is in statistical physics books. If we write that u is equal to f minus t d f s, that is this things here, df over d beta, beta divided by t. So t simplify, and we have, sorry, f is equal to u minus t dot s, so f plus beta df over d beta is equal to u. And so you can see that this is a d over d beta of beta f. And this is u, and we have seen that u is 1 over n d over d beta of logarithm of z. So this is minus 1 over n logarithm of z d over d beta. And from this you get that beta f is equal to minus 1 over n logarithm of z, or that f is 1 over beta. There are many ways to show this. The important thing is the relation between the free energy and the vibrational energy, u minus ts, and s is minus df over dt. So with this basically two formula and an expression for the logarithm of z, we can get the expression of the u, the logarithm of z we have calculated here in two forms at least, and if we derive with respect to beta, we obtain this expression here of the average vibrational energy. And if we simply divide by beta, so this expression divided by beta and n and change sign is the free energy. You have to change sign, divide by beta, and divide by n. And this is the expression of the free energy. And then once we have basically the vibrational energy and the free energy, the entropy is given by this. Now all this sum over, so all these expressions are sum over q and nu. Sum over q and nu of some function of omega of q and nu, and 1 divided the number of cells. So we can calculate like this, simply doing calculating a very thick mesh of Q point and frequency in reciprocal space, interpolating all this mesh of Q point, the dynamical matrix, diagonalizing and obtaining the frequency in this thick mesh, and then doing the sum. We are doing these summations. Or we can calculate the so-called vibrational density of state. That is, we insert here a delta of omega minus omega q nu. Here we put omega and integrate for omega that goes from 0 to infinity. And this is an equivalent expression of our original, let's say this quantity was Q, of our original expression. And the object that we need is the so-called vibrational density of state per cell. In this case, it is per cell. It is 1 divided by n, sum over Q and nu of delta of omega minus omega Q nu. So we could do, once we have the frequency, only once this sum over the Brillouin zone, obtain the vibrational density of state, and with this function, all the quantity Q is equal to the integral of f of omega, g of omega, d omega, from 0 to infinity. And so with formula like this, we obtain the free energy. Here we use the formula with the parabolic sign. The vibrational energy. There is also an expression of the entropy if you want, but we can also obtain as a difference like this. And basically the question is to do an integral over the Q vector in the Brillouin zone and to get the vibrational density of state. Then we have the total energy and the free energy at that given geometry. We can also calculate the constant volume specific heat. It is the derivative of the energy with respect to the temperature. And so it has, if you do the derivative now, we have the expression of U. If you do the derivative, you obtain something like this. This is another equivalent expression. And integrating with the Phonon density of state, we can get this four function. Free energy, vibrational energy, entropy, and specific heat. An important point, these formula are valid if all your frequencies are positive. So it requires that you have a stable system. You cannot use this kind of formula if you have some frequency that is imaginary. An example where this kind of expression have been used has been in the study of the structural transition of beta-tin. Beta-tin at a temperature lower than 13 degrees centigrade it has the alpha structure. It is as a silicon with the same zinc, the same diamond structure with 2 atoms per cell and a cubic unit cell. At 13 degrees, it has a phase transition where you see that the tetragonal cell there that in the alpha phase have a C that is the square root of 2a, get compressed. Square root of 2 is 1.4 something. That C becomes 0.55a. So it compresses a lot. And you obtain the so-called beta phase of T. So if you compare the free energy as a function of temperature, the free energy of the beta phase and the alpha phase, you see that at 0 temperature, the alpha phase has lower energy and is favored with respect to the beta phase. And then, since the entropy of the beta tin increase faster than the entropy of the alpha tin, what happens is that as you increase the temperature, the free energy of the beta tin at a certain temperature goes below the free energy of the alpha tin. So using this function and comparing for different structure in the literature, they have found a reasonable transition temperature for this transformation by comparing the vibrational free energy calculated, however, at fixed volumes. So this is just one calculation of Phonon. With the Phonon, you get the thermodynamic function, you compare them, and you find which phase is more stable than other phases as a function of temperature. These are entropy-driven phase transition that you can study with this method, in which, however, you neglect completely the effect of thermal expansion, of change of volume of your system. Now, next question that I'd like to understand now, we have seen what we can do if we have the frequency calculated at one fixed geometry. What happens if we calculate frequencies at different geometries? So we can try to study what happens changing the Phonon changing the volume or the shape of our unit cell, and calculating the Phonon frequency. Which kind of thermodynamic can we do? Well, we can obtain the quantities that are within the quasi-harmonic approximation. Well, the first question that we can try to answer is, can we obtain the equilibrium volume of a solid as a function of temperature? So I think you have seen how computing the total energy as a function of a volume and minimizing the total energy, you find the equilibrium volume at 0 temperature. So how can we generalize this concept and calculate the equilibrium volume at a given temperature? Well, I think there are a lot of ways to see this. I find this reasonable. It depends on your background, probably. This is a demonstration like this. It says, consider a solid at temperature. So what is the purpose? The idea is that if we want to know at a given temperature what is the equilibrium volume, we can calculate the equation of state for our solid. So we calculate the pressure as a function of temperature. And at each temperature, let's say, we calculate the pressure as a function of volume and find what is the volume for which the pressure is 0. That will be the equilibrium volume at that temperature. And so the idea is this, that if I have a solid that is at a given pressure P and a given temperature T, then if the pressure is constant, the work that is done by the solid is P multiplied by the omega if we change the volume of the solid of the omega. And if we want to keep constant the temperature, we have to give some heat to the solid, and the heat can be written in terms of the entropy. So the change of entropy of the solid will be dQ, the heat that we give divided by the temperature, or if you want, the heat that we give is T multiplied by S. And so the change of the internal energy of the solid will be minus the work that the solid has done. This is the first principle of thermodynamics, plus the heat that we give. So this is the change of internal energy for this change of volume. And from this, we can get the pressure. We divide by the volume. So we have that du is T ds minus P d omega. So we divide by the omega, and we have minus P equal du over the omega minus T ds over the omega. So if you want, P is minus this. So at T equals 0, P would be the derivative of the internal energy divided by omega. At a finite temperature, we have also this term that contains ds over d omega. And actually, this is minus df over d omega, because f was u minus t multiply s. And so this is df over d omega at constant temperature, if we keep the temperature constant. And so if we search for a solid where the pressure is 0, we see that we have to, at the given temperature T, we have to minimize the free energy with respect to the volume. At the minimum of the free energy with respect to the volume will give us the equilibrium volume of our solid. And so the idea of the quasi-harmonic approximation is that we calculate the free energy. We have seen how to calculate the free energy from the Phonon frequency. We calculate the free energy for several volumes. And so exactly as T equals 0, we minimize the energy with respect to the volume. At the finite temperature, we minimize the free energy at that temperature with respect to the volume. So basically, the free energy will have the vibrational term that we have discussed so far, and plus the energy of the electronic part, that is the one given U0 of omega, that is the one given by the DFT total energy. In principle, we should also add the electronic excitation energy, but this is usually small, and we do not consider it in the following. It is not, at least to do some model that keep into account for that correction is not much difficult. But basically, once we have the free energy like that, as a function of the volume and as a function of volume, basically, for each temperature, we can minimize it. For instance, then we will discuss in a moment how to minimize it, and we will have the volume as a function of temperature. The derivative of the volume with respect to temperature divided the volume is the thermal expansion. So from this, we can get immediate, by a numerical derivation of the volume with respect to temperature, the thermal expansion. So to fit the free energy as a function of the volume at a given temperature, for instance, at T equals 0, for instance, one can use a Murnaghan equation that is an equation of state obtaining by introducing the bulk modulus, that is the inverse of the compressibility. Compressibility is how much the volume changes when you apply a pressure divided the volume. And its inverse is called the bulk modulus. If you assume that the bulk modulus has a constant derivative with respect to the pressure, you obtain an equation of state like this. And this will contain three parameters: the equilibrium volume, the bulk modulus, B0, and B0 prime, the derivative of the bulk modulus with respect to the pressure. One way could be to use just this at finite temperature and use this equation for fitting the free energy instead of the energy. And we will obtain the volume as a function of temperature, the bulk modulus as a function of temperature, and its derivative as a function of temperature. Or we can fit this at 0 temperature, use a polynomial for the vibrational part, and then minimize this function plus a polynomial. As you like, the results are not very different. And we can minimize the free energy with one of these fitting functions. So there is another interesting point that I would like to mention. Let me see, what time is it? Maybe much later. I will discuss this, and then I will stop. So thermal expansion from Grüneisen parameters. So instead of doing the procedure that we have seen before, minimizing the free energy and calculating the thermal expansion with an expression like this, what you can do is to use some relationship. You can derive, instead of deriving with respect to temperature, you can derive with respect to pressure, and then at a constant temperature, and then the pressure with respect to T at constant omega. There is this equation is true, but there is a minus sign. And this object is the bulk, 1 divided the bulk modulus, so it is the compressibility at the temperature T. Instead, the pressure as a function of temperature, well, basically the pressure was minus the derivative of the free energy with respect to the volume. And so we have to take the expression of the free energy that we have already written and makes a second derivative with respect to temperature and volume. The result is this, that you will need to compute the derivative of the Phonon frequency with respect to the volume. They are called the Grüneisen parameters. And from Grüneisen parameter and another expression that enters in the expression of the constant volume specific heat capacity, an expression like this in terms of the Phonon frequency, you can calculate the thermal expansion with the product of the Grüneisen parameter and this CQV coefficient, and dividing by the bulk modulus. So in principle, this thermal expansion calculated like this, and the one that you calculate directly from the derivative of the volume with respect to omega should coincide. And in the exercise this afternoon, probably you will see that it coincides if you use the temperature dependence of the bulk modulus. Otherwise, there is a small discrepancy. And also, if you calculate the Grüneisen parameter at the volume that corresponds to a given temperature. Why it is interesting to calculate the thermal expansion and these kind of quantities? Well, basically because experimentally it is easier to keep a constant pressure and not the volume. So we calculated from the Phonon frequency the heat capacity as a function of volume, but it is easier to measure the heat capacity as a function of pressure. So at constant, we calculated the heat capacity at fixed volume, but it is easier to measure the heat capacity at fixed pressure. And there is an expression like this that link the two, that contain the bulk modulus, the volume, and the thermal expansion square. And also sometimes the bulk modulus is measured without heat exchange, and this means at constant entropy. And there is a relationship between the bulk modulus at constant entropy and at constant temperature. I think I will stop here. I just maybe tell you this, and then all the rest you find in the transparency if you are interested. So can we use this kind of approach for anisotropic solids? Well, what is the problem? Because in cubic solid, to change the volume means changing the lattice parameter. And there is a one-to-one relationship between volume and lattice parameter. In other solids, for instance, tetragonal or hexagonal solids, you have two parameters, A and C. In trigonal solid, you have A and the cosinus of the angle, and so on. In orthorhombic solid, you have three parameters. And so when you calculate this quantity as a function of volume, you have to to say what you do for the different parameter. You can change the A parameter and keep the ratios and the angles constant. This is an approximated way. Or you can fix the volume and optimize all the other parameters. The correct way to do this thermodynamics would be to make a more general free energy scheme that contains stress and strain. I will stop here. I had here also the definition of stress and strain, but I think we can stop now because it's already very late. You can find here, if you want, the thermodynamic for anisotropic solids. And in any case, it will not be done in the exercise, so I will stop